Hello, everybody. We're taking a look at the section 7.3 on Achieve, where we're looking at trigonometric substitution. Now, unfortunately, a lot of the problems that's in Achieve when we're doing this trigonometric substitution are going to require the use of table integration formulas. That's not always the case, but it just seems like quite a few of the problems that's on Achieve end up being that way. So not crazy about the problems within this section, but we'll make the best out of them. Okay, for example, with this first problem here, you can see that they're asking us to integrate x squared over the square root of 169 minus x squared from 0 to 13 over 2. Now you can already see where I got that answer correct. Let me show you where that came from. All right, so in this problem here, I went ahead and just worried about the indefinite integral first. I didn't want to worry about the limits of integration from the very onset of the problem. So I'm integrating x squared over the square root of 169 minus x squared. And I'll go ahead, their suggestion for the substitution was the correct one. Anytime you see a squared minus x squared, you're supposed to let x equal a sine theta. Well, the square root of 169 is 13. So I'm going to let x equal 13 sine theta. Now dx, well, the derivative of 13 sine theta is 13 cosine theta with respect to theta. Now I can say, well, all right, once I get that dx substituted in here along with the x, this problem is going to work itself out. I have the x squared, I know that's just 169 sine squared theta, times dx. Well, my dx is my 13 cosine theta, and I left my d theta at the end. My denominator, I've shown down here how that square root simplifies in this problem. The square root of 169 minus x squared becomes the square root of 169 minus 169 sine squared. Then what you're supposed to do is say, well, I know I could factor out 169 on the inside, and I would be left with 1 minus sine squared. You know 1 minus sine squared is cosine squared, so the inside of that root would be 169 cosine squared x. Both of those factors have a perfect square root, so we take that and we say that's just going to be 13 cosine theta. Now, that becomes the denominator of my expression, and we quickly see that cancels with a term in the numerator. The 169 I can factor out front, and then the only thing that's left on the inside is the sine squared theta d theta. So I can say, well, once I do that sine squared theta d theta there, I can then go in and say, well, that's just going to be the power reduction formula. And what I did from this step to this step is use that power reduction formula. Let me try to make this a little more clear over here. Yeah, there we go. I used that power reduction formula. I said the reduction formula for sine squared, and this is a trig identity, it's 1/2 times the group, 1 minus the cosine of twice the angle. Well, the angle is theta, so twice that angle is just 2 theta. Now, I can integrate this. What I did from this step to the next is I said, well, that 1/2 I can just bring to the outside and call it 169 divided by 2. And then I'll have the integral of 1 minus cosine 2 theta. Well, the integral of 1 with respect to theta is just theta. The integral of the cosine of 2 theta is going to be the sine of that angle, 2 theta, divided by the derivative of the angle, 2. Now I need to simplify that because I'm not going to be able to put this back in terms of x if I leave this angle 2 theta. So here in red, I'm showing the double angle identity. Well, the sine of 2 theta is equal to 2 sine theta cosine theta. So what I've done from this step to this step is replace that numerator with 2 sine theta cosine theta. Of course, this 2 in the numerator cancels with the 2 in the denominator, and I just have minus sine theta cosine theta. Now, the answer to the integral in terms of theta would be 169 over 2 theta minus the sine of theta. Well, I need the answer in terms of x. So I went back and I said, all right, then my definite integral, which is what I was trying to do in the original problem, is going to equal The integral from 0 to 13 over 2, x squared over the square root of 169 minus x squared, integrated with respect to x. I still keep my 169 over 2 out in front. Now, what's theta? Well, theta you can easily solve because we know that the trig identity, the trigonometric substitution that we used was x was equal to 13 sine theta, which means x over 13 is equal to the sine of theta. So now if you try to solve for theta, you say, well, I can solve for theta by just taking the inverse sine of both sides. The sine of theta is x over 13, then theta is equal to the inverse sine of x over 13. That's where that came from. I took the inverse sine of both sides and got theta is equal to the inverse sine of x over 13. Now, this next portion here that I had to simplify to be the sine theta cosine theta, and it's still being subtracted. Well, I already know that the sine of theta is x over 13. That's from my trig substitution, so I could put that in. To get what the cosine of theta is equal to, you draw your trig triangle, and you say, well, if the sine of theta is x over 13, then inside of a right triangle, we know that the ratio of the opposite to the hypotenuse is x over 13. So I said, knowing that the sine of theta is x over 13 allows me to say that the opposite side is x and that the hypotenuse is 13, which now means I know that the adjacent side is just the square root of the hypotenuse squared minus the other side squared. So 169 minus x squared. Please do keep in mind in your trig triangles, the expression from the original problem always must pop up in your trig triangle. If it doesn't, you're doing something wrong. So as soon as I saw that square root of 169 minus x squared in my trig triangle, I knew I was on the right track. Now I go in and I can say, all right, well, the cosine of theta, that should be adjacent over hypotenuse. That's where this came from, the square root of 169 minus x squared over 13. Now I needed to evaluate this expression since I have it in terms of x, from x equals 0 to x equals 13 over 2. When I plugged in the 13 over 2, 13 over 2 divided by 13, that's just going to be 1/2. And then I was thinking, well, the inverse sine of 1/2, that's just saying, when is your sine function 1/2? That's going to be at pi over 6. That's when the y value in the unit circle is at a rate of 1 over 2. So that's where that angle came from. And then for my second one, when I plugged a 13 over 2 here, you get 13 over 2 divided by 13. That's going to be 1/2. I plugged a 13 over 2 into this expression, and I got the decimal 0.866, which when I multiplied by 1/2 gave me this over here. So this is the inverse sine of 1/2 minus 13 over 2 plugged into the second term there. The lower limit of integration is irrelevant because it would be the inverse sine of 0, which is 0, and then it would be minus 0. So I just get a 0 for that lower limit. Achieve wanted a 3 decimal place answer on this, so I just plugged this in, 169 over 2. I kept 6 decimal places within the problem to make sure that my answer would be 3 decimal place accurate, and you can see now on Achieve, it liked that 3 decimal place accuracy, which is what it was asking for. Now, in your next question here, they're again telling you what the trig substitution needs to be in the problem. I really wish they wouldn't do that. We need to be able to figure out what the trig substitution is. But in this one, you have 1 over x on the square root of x squared minus 9. Anytime you have a variable squared minus a constant squared, you're going to say let x equal a times the secant of theta, where a is the square root of this constant, because that's x squared minus a squared. So you say, well, then a is 3, and x is going to equal 3 secant theta. If you're going to use the trig substitution that x is equal to 3 secant theta, then we need to account for dx. dx is the derivative of that, 3 secant theta tangent theta with respect to theta. I also went in and showed that that square root is going to become the square root of 9 secant squared theta minus 9. Inside that root, you could factor a 9, and it would be the square root of 9 times secant squared minus 1, which is 9 times tangent squared theta. The square root of that would be 3 tangent theta. So now I'm ready to plug back into my problem. Your numerator is just the dx. Well, here's your dx, 3 secant theta tangent theta. I'd prefer to put the d theta at the end, though it could go in the numerator. Your denominator is x, which is 3 secant theta, times that square root, which I've shown down here is 3 tangent theta. From this step, I said, well, I know that this 3 can cancel with one of the 3's in the denominator, but I'll still need to pull out a factor of 1/3. The secants are going to cancel, the tangents cancel. Now, wow, everything cancels other than the factor of 1/3, which I pull out. So all of this reduces down to just a 1 with respect to theta, which is very easy to integrate. The integral of 1 with respect to theta is just theta. So we'll get 1/3 theta plus c. Well, how do we solve for theta? We know our original trig substitution is equivalent to saying x divided by 3 is the secant of theta. Therefore, theta is the inverse secant of x over 3. And I get 1/3 inverse secant of x over 3 plus that glorious constant of integration. And you see, that's precisely how Achieve wanted that answer on that question. For the next question here, number 3, it's asking us to integrate a definite integral. We have dx over x squared on the square root of x squared plus 100. As soon as you see that x squared plus 100, again, I wish they wouldn't have told us, but we should have known to use the trig substitution to let x equal a tangent theta, in this case 10 tangent theta. So whenever I show the work I did for this problem right here, I have the integral of dx over x squared times the square root of x squared plus 100. X squared plus a squared tells me x needs to equal a tangent theta. Well, that's going to be 10 tangent theta. Dx, derivative of tangent, is secant squared, so I get 10 secant squared theta d theta. I need to find out what dx is so I can substitute it back into the problem. Dx in this case, I need to find out what the square root is. I already found out what dx is. The square root of x squared plus 100 becomes 100 tangent squared plus 100. Inside that root, I would have 100 times tangent squared plus 1. That's 100 times secant squared. The square root of 100 is 10. The square root of secant squared is secant. So now I know everything in the problem. I go ahead and I substitute dx in my numerator, 10 secant squared theta d theta. My denominator, x squared, that's going to be 100 tangent squared theta times the square root. We've already shown the square root down here is equal to 10 secant of theta. So now I try to simplify. I know this 10 and that 10 will cancel each other out. So I can factor this 100 out in the denominator and get 1 over 100 on the integral of, and then inside of this fraction, I'm going to have the secant of theta. That canceled with 1 power of secant in the denominator. Secant squared over secant gave me secant in the numerator. And that tangent squared did not cancel out in the denominator. So I have secant theta over tangent theta, and I need to integrate this with respect to theta. Okay, so now over here, I keep my 1 over 100 out in front. I don't see a nice way to integrate this as is. If you were thinking a substitution here, like, hey, what if I let u equal tangent theta? It wouldn't work well because then du is secant squared. You don't have that. On the other hand, if you let u equal secant, yes, du is tangent squared theta, but that's tangent squared times d theta, not d theta divided by tangent squared. So substitution would not work nicely in this format. However, if I rewrite secant as 1 over cosine, and I know tangent squared is sine squared over cosine, but if you divide by a fraction, then you're multiplying by that fraction's reciprocal, so it becomes times cosine squared over sine squared. Glorious. Now I can see this cosine is going to cancel out one of the cosines in the numerator, and I'll bring it down here and simplify and say I keep my 1 over 100 on the outside. I'll have 1 factor of cosine left in the numerator over a sine squared in the denominator. Immediately I can see that substitution is helpful now. So I can go ahead and say, let's let u equal the sine of theta. Well, then du is cosine of theta d theta. Glorious. All that becomes du. And then I get 1 over u squared du, which I would prefer to call u to the negative 2 du. We can integrate that by the power rule and call it u to the -1 over -1, which that's kind of sloppy. So I would say, well, that's better written as -1 over 100, u to the first. Now that's in terms of u. Well, what if I back substitute? I know u was the sine of theta, so this is equal to -1 over 100 sine theta. Then I back substitute again and say, yeah, but now I need to get rid of that sine theta. Well, I go to my trig triangle. You use your initial trig substitution to construct this trig triangle here. You cannot leave this answer in terms of theta. So then I can say, well, all right, I know I set x equal to 10 tangent theta, which means x divided by 10 is the tangent of theta. What do you know? Well, you know theta is an angle inside of a right trig triangle in which the opposite side is x and the adjacent side is 10. I used that to construct the opposite and the adjacent since I knew tangent of theta was x over 10, which now means the hypotenuse is just the square root of this side squared plus this side squared. And yet again, please remember, an expression from the original problem must pop up in your trig triangle or else you're wrong. Well, we're right. So now I have my trig triangle. I go back in and I can say, well, I have -1 over 100 times the sine of theta. If I look at my trig triangle and say, well, what's the sine of theta? Sine of theta would be opposite over hypotenuse. So in that denominator, I would have the fraction x over this root. Well, if you're dividing by a fraction in the denominator, then why not multiply by the reciprocal of that fraction? That's what I did. So instead of dividing by x over the root, I said, let's multiply by the root over x. That's where I got this answer. The -1 times the root of x squared plus 100 over 100 times x. Much cleaner than leaving that ugly fraction in the denominator. Now, I know this is my answer with respect to x. The original problem was not just the indefinite integral, though. It was the definite integral. So I'm trying to keep my notation perfect here. I can say, so the original problem that had the definite integral is equal to our answer in terms of x evaluated from 1/2 to 1. When you plug the 1 into that expression, you get the negative square root of 101 over 100. When you plug the 1/2 into that expression, the positive came from, you always subtract the lower limit, but the lower limit is negative, so minus a negative is plus a positive. And I get the square root of 100.25, 1/2 squared is 0.25. And my denominator is just 50. Well, I added these together, achieved one at a 3 decimal place answer, which I really didn't like in this case. I wish it would have went 4 decimal places or something, but 3 decimal places, if you're rounding there, then that 7 rounds the 9 up to a 10, which rounds that 9 up to a 10, which just makes this a measly little 0.1 to 3 decimal places, which you'll see is precisely what Achieve wanted for that one. Now the next one here, we're moving away from definite integrals back towards indefinite integrals, and fortunately they did not tell you what your x substitution is in this one, but that should be extremely easy. What you do is you look at it and you say, well, every single time you have a squared minus x squared, we let x equal a sine theta. Well, 361, that's 19 squared. So x is going to equal 19 sine theta in this problem. You'll see that's what I did right here. Nice. So we have the integral of x squared over the square root of 361 minus x squared integrated with respect to x. I let x equal a sine theta. A is just the square root of that number, 19 sine theta. Good things should happen now. Well, dx, derivative of 19 sine theta is 19 cosine theta with respect to theta. Then I can say, well, all right, let's figure out what that square root is. Square root of 361 minus x squared is the square root of 361 minus 361 sine squared theta. Now, what I would do inside of here is I'd say, well, this is equal to 361 times 1 minus sine squared. 1 minus sine squared is cosine squared. The square root of cosine squared is cosine. Square root of 361 is 19. Now all of that would simplify to just be 19 cosine of theta. I go back into my problem. X squared, that's going to be 361 sine squared theta times dx. Well, that's your 19 cosine of theta d theta. Your denominator, I've already shown my denominator, that root is equal to 19 cosine theta. That 19 cosine theta cancels with a 19 cosine theta in the numerator. We can factor out the 361. Similar to the first problem in this assignment, we're left with sine squared. What you're supposed to remember at that point, you cannot integrate sine squared as it is. You cannot integrate any power of a trig function as is. So we just say, well, all right, we're going to use our power reduction formula that says sine squared is equal to 1/2 times 1 minus the cosine of twice the angle. I used that here in this problem. You'll see the 1/2, I just went ahead and factored to the outside and said the integral of 1 minus the cosine of 2 theta. Makes it extremely easy to integrate. That's what I've done down here. I stands for the original integral. The original integral is equal to 361 times the integral of 1. Well, that's theta. The integral of cosine 2 theta, well, that's going to be the sine of 2 theta over 2. And here's where I have to use, yet again, another trig identity, because it's impossible for me to get back in terms of x if I have that angle 2 theta. I don't know anything about the angle 2 theta. However, I do know information about the angle theta because of this right here. So I can say, I need to get this back in terms of theta. Yes, I had to put it in terms of 2 theta to integrate it, but now that I've integrated it, I need to put it back in terms of theta. I use the double angle identity. Sine of 2 theta is 2 sine theta cosine theta. This 2 and the 2 in the denominator cancel. And you'll be left with 361 times theta minus sine theta cosine theta, plus your constant of integration. Can't forget that since this is an indefinite integral. Now I can say, well, what is theta in this problem? My trig substitution was x is equal to 19 sine theta, which means the sine of theta is equal to x over 19. So if I said, hey guys, use this equation to solve for theta, well, theta would equal the inverse sine of x over 19. That's what I put right there. 361 over 2 times theta is 361 inverse sine of x over 19. Now I distributed that 362 into the second term. I have minus, I should have said 361 over 2, minus 361 over 2 times the sine of theta. We already know that's x over 19 times the cosine of theta. Well, the sine of theta being x over 19 told us the opposite and the hypotenuse of our trig triangle. Well, then I know that the adjacent is the square root of the hypotenuse squared minus the other leg squared, and I get the square root of 361 minus x squared there. So then the cosine of theta would be adjacent over hypotenuse. That's where this right here is coming from. Now I need to simplify this gloriously beautiful answer. I know these two 19s would multiply to get 361. That's going to cancel out that 361. So I'm just going to have 1/2 x times this square root here for that second term. And I already had the first term done, plus your constant of integration. You'll see that this is precisely how I entered it in on Achieve, and Achieve liked it. Next question here for number 5. We have the integral of 1 over y on the square root of 6 minus y squared integrated with respect to y. So as soon as I see this one, I'm thinking, all right, I have a squared minus y squared. And true, 6 is not a perfect square, but that's okay. You could say, well, that's the square root of 6 squared minus y squared. Anytime you have a constant squared minus a variable squared, you're going to say, I need to let that variable equal a, which is the square root of 6 in this case, times the sine of theta. So you'll notice, as soon as I started my work here, boom. I have the original problem, and I said, I need to let y equal the square root of 6 sine theta. If I do, I guarantee you things are going to work out. All right, well, dy. Derivative of y is going to be the square root of 6 cosine theta d theta. Now I'm just showing what that square root is going to equal when I go back and substitute into the problem. We know that 6 minus y squared would be 6 minus 6 sine squared y. You could factor a 6 inside of that root and have 1 minus sine squared, which is cosine squared. The square root of cosine squared gives me cosine, square root of 6, square root of 6. So that square root is going to simplify to be the square root of 6 cosine theta. As soon as I do that, I go back into my problem, your numerator. Square root of 6 cosine theta d theta. Your denominator, y squared, becomes 6 sine squared times that square root, which we already know is the square root of 6 cosine theta. Now, I know that this root of 6 and this root of 6 in the numerator will cancel. You'll be able to factor out a 1 over 6 in front of the integral. And then inside the integral, you're going to be left with 1 over sine squared theta d theta. Everything else canceled. Then you can say, well, 1 over sine squared, that's the same thing as cosecant squared. And then you have to go back to your trig knowledge and say, well, I know that the derivative of cotangent is negative cosecant squared. All right, then the integral of cosecant squared is a negative cotangent. That's why from this step to this step, it went from positive to negative 1/6 cotangent theta plus your constant of integration. Now, we needed the answer back in terms of y. That's where this comes from. And I can say, well, in order to get to that, I needed to draw my trig triangle. Where do you get your trig triangle? Always, always from your original substitution that you did in this problem. So you know that y is equal to the root of 6 sine theta. So I can say, well, then y divided by the root of 6 should equal the sine of theta. All right, then that allows me to say inside of a right trig triangle, the side opposite theta needs to be called y. The hypotenuse needs to be called the root of 6. Yes and yes. Now, the other side is going to be always the square root of the hypotenuse squared minus the other leg squared, 6 minus y squared. And again, remember, an expression from the original problem must pop up in your trig triangle. If it doesn't, you're wrong. I go back and I now plug in what I know. Negative 1 over 6 cotangent theta is going to become negative 1 over 6 times cotangent. Well, we know tangent is the ratio of opposite over adjacent. So cotangent is the reciprocal of that. It's going to be adjacent over opposite. It's the square root over y. That's where that came from, adjacent over opposite. And then I'm just simplifying, although nothing cancels, I just rewrote it in a little nicer format and said it's the negative square root of 6 minus y squared, all divided by 6y plus your constant of integration. And when we check that with what I entered in on Achieve, you see, yes, absolutely what they wanted. For the next question here, number 6, we were given the problem, the integral of dz over z cubed on the square root of z squared minus 4. As soon as I see variable squared minus constant squared, I'm thinking, okay, this is a secant theta, where a in this case is the square root of 4, 2. So z is going to equal 2 secant theta. dz, 2 secant theta tangent theta, d theta. Now let's go in and figure out what the square root is. The square root of z squared minus 4 becomes the square root of 4 secant squared theta minus 4. We know that that's going to be 4 times secant squared theta minus 1. Secant squared theta minus 1 is tangent squared theta. So the inside becomes 4 tangent squared theta. The square root of that is going to be 2 tangent theta. I'm ready to go back into my problem and substitute back in. My numerator just becomes the equivalent of dz. My denominator, z cubed, is going to be 8 secant cubed theta times the square root, which we know is 2 tangent theta here. Now, we know that the 2 in the numerator and denominator, surely those cancel, but that 8 is not going to cancel, so I'll just move it to the outside as a 1 over 8. Now I can see that the secant and the tangent cancel out in the numerator. The tangent cancels out of the numerator and denominator. When I cancel out the secant in the numerator, it's going to leave me a secant squared in the denominator. And I can say, well, the inside is just 1 over secant squared theta d theta. As soon as I do that, I don't know how to integrate 1 over secant squared. So I just say, well, secant's nothing more than the reciprocal of cosine. So if you have 1 over secant squared on the inside, then you have a cosine squared on the inside. And this I do know how to integrate, but first I would have to use the power reduction formula. Cosine squared theta is going to be 1/2 times 1 plus the, and keep in mind the difference in it in our formula that we had for the sine. In the sine formula, you always say to power reduce sine, it's 1/2 times 1 minus the cosine of twice the angle. Now for the cosine, it's 1/2 times 1 plus the cosine of twice the angle. So you say, okay, that's no problem. That 1/2, I'll have to factor it out and call that 1/16 on the outside. And then we have our integral of 1 plus the cosine of 2 theta. Well, the integral of 1 with respect to theta is theta. The integral of the cosine of 2 theta is just going to be the sine of 2 theta over 2. And then I can say, all right, yet again, in order to get this back in terms of z, I can't have that 2 theta there. So I use the double angle theorem. It says the sine of 2 theta is equal to 2 sine theta cosine theta. This 2 and this 2 cancel, and this is just going to become theta plus sine theta cosine theta on the inside. Both of those gets multiplied by 1/16. So that's where this came from, of course, plus the constant of integration. Now, when I go back into the problem, in order to construct the trig triangle, I know that z divided by 2 would equal the secant of theta. It may help you to remember, well, the cosine is just the reciprocal of that, so the cosine of theta would equal 2 over z. So now I can go in and construct a trig triangle and say, well, the side adjacent to theta has to be 2, the hypotenuse has to be z. So then my other leg is the square root of the hypotenuse squared minus the remaining leg squared, z squared minus 4. And again, something from your original problem must pop up in your trig triangle, and it did. For the first part, no problem. 1/16 theta, I could say, well, theta is the inverse secant of z over 2. I could also call theta the inverse cosine of 2 over z. Either way, it's correct. Since I did a secant substitution, I just kept it in terms of inverse secant, and I said theta is equal to the inverse secant of z over 2. But it is important to remember that since secant and cosine are reciprocals of each other, if you want to do the same thing in terms of inverse secant and inverse cosine, you just have to take the reciprocal of the argument. So the inverse secant of z over 2 is equal to the inverse cosine of 2 over z. Now, for the second part of this, I said 1/16 times the sine of theta. Well, the sine of theta, that's going to be opposite over hypotenuse, the square root over z there. The cosine of theta, 2 over z, 2 over z. In simplifying this, I left the first term alone. That second term, the 2 and the 16 reduced down to 1 over 8. So I have an 8 in the denominator along with the z squared. And my only numerator is that root of z squared minus 4. So we have that really nice answer. And you'll see that's precisely how I entered it into Achieve. And Achieve was agreeable with that answer. The next question here, we have the integral of, and this one did have some, so make sure whenever you're entering your answer in for this number 7, you're careful. I'll explain that when I get to it. We have the integral of x squared integrated with respect to x over 7x squared minus 9 to the 1/2 power. All right, so this one, very, very tricky. What I'll need you to do is whenever you're saying let x equal a tangent theta, you could have went ahead and factored out the square root of 7 out of that group. You could have. I chose not to. What I would like you to remember, anytime you're trying to find a, instead of just taking the square root of this number, which it is the square root of that number, but then it's always divided by any coefficient in front of the x squared term. So you say, well, then a squared is going to be 9 over 7. If a squared is 9 over 7, then a is the square root of 9 over the square root of 7, which simplifies to be 3 over the root of 7. So I have x is equal to 3 over the root of 7, and anytime it's a variable squared minus a constant squared, it's a secant theta. So I get 3 over the root of 7 secant theta. Derivative of that, well, I get 3 over 7 secant theta tangent theta d theta. Now, the reason that this trig substitution works, and this should be evidenced right here, is when you plug it back in for x, it's going to simplify out that expression. If you say, well, if I let x equal 3 over the root of 7 secant theta, 3 over the root of 7 squared is going to be 9 over 7. 9 over 7 times 7 is 9, and I would have the secant squared theta minus 9. Now, the inside of that group, you could factor to be 9 times secant squared theta minus 1. Secant squared theta minus 1 is tangent squared theta. 9 times tangent squared theta inside the 1/2 power just gives me 3 tangent theta. Gorgeousness. Now we can say, all right, let's go back and substitute into our problem. We have the x squared. Well, that's this group right here, 9 over 7 secant squared theta dx. That's this right here, 3 over the root of 7 secant theta tangent theta, the d theta I put at the very end. All divided by that group to the 1/2 power, which I've shown is just equivalent to 3 tangent theta. All right, so now this 3 can cancel out the 3 in the numerator, but I still have 9 over 7 on the root of 7 in that numerator. I went ahead and factored that constant out. That's where this came from. Now, the tangent theta cancels out the tangent theta in the numerator, but I'm still left with secant squared theta times secant theta. And so the inside of this integral is the secant cubed theta. Now here's where, for the very first time in these problems, and it happens quite a bit after this, we have to, and I hate doing it, but we have to rely on our table of integrals. I have it posted online for you. Actually, it's linked right here. So in your D2L course, it's under the notes from lecture videos. And if you go to right before the, or right in between what's going to be 7.2 and I'll do 7.3 lecture notes. So right before the lecture notes for this section in 7.3, you can see the integration table from the back of the book. You could also just, I'll show you the address here. It's a pretty simple address. It's off of my faculty webpage. It's psdcc.edu, FactStaff, JWLAM. It's my 1920 content, and it's the integration table. It's actually not as easy of a web address as I thought, but still, it's there. So it's posted online. All it is, it's the back part of your book that has the integration table. So if you don't even want to look at this, just flip to the back of your book, or if you have the paperback loose leaf version, it's at the end of all of your content there. You should see some pages at the end that have this content in there. Now, there are a few typos on this that we will talk about, but those typos are not on this problem. In this problem, you'll see in my work here, and this is how ideally you would always designate your work. Unfortunately, for this class, I won't be able to see your work for these questions. You'll just be entering a question in Achieve and either getting it right or wrong. But if you were submitting work and trying to show somebody how you're getting from one step to the other, anytime you use something from an integration table, you're supposed to designate it over the equal sign. I'm using integration table number 42 right here. And so you can go to your table of integrals and you can see, I'll scroll down here. Maybe my computer will allow it. There we go. When I scroll to 42, you'll see, hey, yeah, secant cubed u du, the integral of that is equal to 1/2 secant u tangent u plus 1/2 the natural log of secant u plus tangent u plus the constant of integration. So now you can see that that's precisely what I've done. Now, of course, I can't put u because my angle was theta. So the integral of secant cubed theta is 1/2 secant theta tangent theta plus 1/2 the natural log of secant theta plus tangent theta, all in an absolute value, plus your constant of integration. Now, of course, we can't have our answer in terms of theta. I needed it in terms of x. So if you just multiply by the reciprocal of 3 over the root of 7 here on both sides, you can see that the secant of theta would equal the square root of 7 times x divided by 3. Now, if the secant of theta is equal to that, now remember, well, secant's nothing more than the reciprocal of cosine. Cosine would be adjacent over hypotenuse, so the secant is hypotenuse over adjacent. So The root of 7 times x is my hypotenuse. My adjacent is 3. Then that means my opposite side, my other leg, has to be the square root of the square of the hypotenuse, which would be 7x squared, minus the square of the leg, which is minus 9. And again, the expression from the original problem must pop up in your trig triangle, and it does. So now I have my 9 over 7 root of 7. I went ahead and distribute that into both terms, and I got 9 over 14 on the root of 7 when I multiplied it by 1/2 here. Secant theta, well, I already knew secant theta was right here, times the tangent of theta. That's adjacent, opposite over adjacent there. And then plus, that distributes to the other 1/2 as well, and I get 19 over 14 root of 7 natural log of the secant, which we already said was the root of 7 over 3, plus the opposite over adjacent, the square root of 7x squared minus 9 over 3, plus your constant of integration. Now, there's a couple of things I want to talk about. My next answer here is actually gorgeous. But Achieve didn't like it. Let's talk about why. So first thing I want to talk about is the simplification. We can see in this first one, these 2 3s cancel with that 9, and I can say, well, this is just better written than this root of 7 canceled with this root of 7. This is better written as x on the root of 7x squared minus 9 all over 14. That's a nice answer there. Plus the second part. And you might be thinking from here to here, I've made a mistake. I have not. What I did is I recognized inside of this natural log, I have a common denominator of 3. So I could write that as the natural log of the root of 7x plus the root of 7x squared minus 9 all over 3. And then anytime you have division inside of a natural log, you can separate that and say, well, it's the natural log of the numerator minus the natural log of the denominator. Why did I not put minus the natural log of the denominator? Well, because it would be minus the natural log of 3, which is just a constant. And for the first time, this is where, and I don't think this is applied into a problem before, this is where they're talking about online where it says absorb into C as much as possible. So what that means is you would never ever put, minus the natural log of 3. Why? Because it's just a constant. So that got absorbed by the constant of integration. That's what they mean whenever they say absorb as much into C as possible. So this goes away since it's just some constant that you're subtracting and it gets absorbed into C. So I just have the natural log of the numerator there for that term. Now, Achieve should, and I say should, have accepted this answer. When I tried to put this into Achieve, it did not accept it. I've contacted the administration to hopefully that they will fix it to where it will be accepting of the correct answer. But just to get you to work this for now, you'll want to leave it in a factored format. So I put, however, Achieve wants it in with factors in front. So it's wanting you to factor out 1 over 14 root of 7. You can see the first term has a factor of 14 root of 7. The second term has a factor of 14 root of 7 in the denominator. So you could just factor out that 1 over 14 root of 7. Now, it really leads to a sloppier answer, but it's the answer that they want. When you factor out that 14 root of 7, your first term, this 9 still cancels with the 9 in the denominator, but you'd have the root of 7x times that, the root of 7x squared minus 9. Your second term, if you're factoring out that 14 root of 7, out of it, you're just going to be left with 9 natural log of the terms that were previously just in the numerator. Denominator still cancels out either way, plus the constant of integration. And now you'll see that that is precisely the format that I have put and that Achieve likes. But for some reason, it did not like what I think this is the better answer here for this problem. It should have accepted this answer, but sadly it did not. So just keep in mind, it's wanting you to factor in this problem despite it being the same answer either way. All right, guys, hopefully this helps out with these problems. The last 4 take a bit longer. I'll do them in another video.